Hello students, today we are starting vector calculus. So first we see what is a scalar point function and a scalar field. If to each point P with coordinates x, y, z, or you can say that with position vector xi cap plus yj cap plus zk cap. In a region E subset RQ means E is a three-dimensional region. So if to each point P in a region E, there corresponds a unique scalar, definite scalar, denoted by phi of P or phi of x, y, z by some rule phi. For every point P, there exists a scalar phi P, unique scalar, definite scalar, means a real number, by some rule phi. Then this rule phi is called a scalar point function. It's called a scalar point function. And we said that a scalar field phi has been defined on E. And we said that a scalar field phi has been defined on E. Or you can say that the region E together with phi is called a scalar field. Okay. So a scalar field is not only a scalar point function, it is together with the region, with the domain on which the function is defined. Function phi is defined. For example, if phi of xyz denotes the temperature at a point, temperature is a scalar. Temperature is a scalar. So if phi xyz denotes the temperature at a point with coordinates x, y, z of a region, then phi is a scalar point function. Another one, if we write phi of xyz equal to x square plus y square plus z square simply for all xyz in R cube, means in the whole three-dimensional space, then this function phi is a scalar point function. Now we define what is level surface. If phi of xyz is a scalar point function defined at each point of a region E subset of R3 and C is an arbitrary constant, then the equation phi xyz equal to C represents a family of surfaces. Why family of surfaces? Because C is an arbitrary constant. It can take various values, infinite number of values. So there is not one surface, infinite number of surfaces. So this equation represents a family of surfaces, and any surface of this family is called a level surface. Any surface of this family is called a level surface or iso-phi surface or an iso-phi surface, you can say. Means phi value is iso, equal, identical, same. For example, if phi xyz equal to x square plus y square plus z square for all xyz in R cube, and C equal to A square is a positive constant. C equal to S square we have written. S square is a positive constant, and also we have taken A greater than 0 here. Then phi xyz equal to C means it is x square plus y square plus z square equal to A square. Instead of C, it is A square. So this equation represents a family of spheres. All of you know this is a sphere. It is a family of spheres because A is arbitrary, with center at origin and radius A, small a. In particular, if we take phi xyz equal to 4, that is x square plus y square plus z square equal to 4 here. 4 means here 2 square. This is a level surface. For particular value of C or particular value of S square here, this equation x square plus y square plus z square equal to 4 represents a sphere with center, origin and radius 2. And this is a level surface. Level surface. There are infinite number of spheres and this is a single sphere, one sphere. So this is a level surface. And why it is called level surface, let us see. We note that for any point on this sphere x square plus y square plus z square equal to 4. For any point on this sphere, the phi value is 4, phi xyz. This is left side is phi xyz. It is always 4. X, y, z are not constant. But phi of xyz is a constant. Means phi value is same for all points on this sphere. So it is 4. And that is phi value is at the same level. Phi value is at the same level, and that justifies the name level surface. Level surface or iso-phi surface. Also we note that for a given point x1, y and z1, there passes one and only one level surface through x1, y and z1. If x1, y and z1 is a fixed point, then passing through this, there will pass one and only one level surface corresponding to a given scalar point function. Of course, if you change the phi xyz, then there will be many various surfaces. But for a given function phi xyz and for a given point x1, y and z1, there passes one and only one level surface. Now we define what is vector point function and vector field. Previously we have defined scalar point function, scalar field, now vector point function and vector field. If to each point p, x, y, z in a region E subset are cube, there corresponds a unique vector. This time there corresponds a unique vector denoted by f bar x, y, z, or you can say f bar p, f bar within first bracket p, f bar p. By some rule f, here rule is f. By the rule f, for every point p, there is a unique vector f bar x, y, z, or f bar p. Then this f bar is called a vector point function. The rule f, no doubt, but with the symbol, vector symbol here, is called a vector point function. And we say that a vector field has been defined on E. Or you can directly say that the region E together with f bar is called a vector field. Vector field is a vector point function together with the domain on which it is defined, region on which it is defined. Okay, so this is vector field. For example, if f bar x, y, z denotes velocity at a point x, y, z of a moving particle, then f bar is a vector point function because velocity is a vector. For every point there is a definite velocity, so vector point function. And mathematically if we write f bar x, y, z is equal to x square I cap minus y j cap plus zx k cap for all x, y, z in R cube, any point, then f bar, this f bar is a vector point function because the answer is always a unique vector for every point. Now we define what is del or nabla operator. Del or nabla operator. The vector differential operator del or nabla is denoted and defined by del. This is del operator symbol with vectors symbol, of course. Del equal to I del by del x plus j del by del y plus k del by del z, means partial derivative. This del x, del by del x is partial derivative with respect to x, del by del y is partial derivative with respect to y, del by del z is partial derivative with respect to z operator notation. So in short we can write it summation I del by del x. So this is called del or nabla operator. It is partial derivative together with vector symbols. Okay. Also for any constant vector a vector, we define a vector dot del equal to a vector dot I cap del by del x plus a vector dot j cap del by del y plus a vector dot k cap del by del z, or in short we can write summation a vector dot I cap del by del x. So this is a vector dot del. This is also an operator. We note that a vector dot del not equal to del dot a vector. Although dot product of vectors is commutative, we know, as because this del is not a vector here. It is a vector differential operator. It is not directly vector, it is a vector differential operator. That's why it is not commutative here. Okay. Then Laplacian operator. What is Laplacian operator? It is denoted and defined by del square. Del dot del square becomes scalar operator here. So it is del square by del x square plus del square by del y square plus del square by del z square. This is the definition of Laplacian operator. It is known as Laplacian operator in 3 dimension, of course. The equation del square phi equal to 0, that is del square phi by del x square plus del square phi by del y square plus del square phi by del z square equal to 0 is called Laplace's equation. Laplace's equation, and any scalar point function phi satisfying this Laplace's equation is called a harmonic function. Harmonic function in 3 dimension, of course. If we omit del square phi by del z square, means in 2 dimension if we consider, that is also a harmonic function in 2 dimension, as we get in complex analysis for definition of harmonic function. With just del square phi by del x square plus del square phi by del y square equal to 0, then phi will be called harmonic function in complex analysis in 2 dimension. For example, if we write phi equal to x square minus s square plus 4z, then this function is a harmonic function. You can easily verify del square phi by del x square will be 2, del square phi by del x square del y square will be minus 2, and del square phi by del z square will be 0. So 2 and minus 2 added 0. So phi satisfies Laplace's equation. Therefore this phi is a harmonic function. Now we define what is gradient of a scalar point function and its geometrical interpretation. Let us see. Gradient of a differentiable scalar point function phi x, y, z defined in a domain E subset of R cube, 3 dimensional region or domain, is a vector point function denoted and defined as phi is a scalar point function. It is differentiable. Its gradient is a vector point function. Okay, and it is denoted and defined as grad phi is equal to del phi, no dot no cross, del phi, del operator operates on phi, equal to I del phi by del x, I cap rather vector, plus j cap del phi by del y plus k cap del phi by del z, or in short we can write summation I cap del phi by del x. So this is gradient of a scalar point function. Answer is a vector point function. The gradient of a scalar point function phi x y z at a point p x on y on z1 on the level surface phi x y z equal to c. Consider the scalar point function phi x y z, then phi x y z equal to c is a level surface or a of course particular value of c, and if x on y and z1 is a point on this level surface, then gradient at this point is a vector normal to this surface at the point p. Of course, if it is not the zero vector. If gradient is not zero vector, then it is a vector normal to this surface at the point p. See here. This is the surface, px on y and z1 is a point on the surface. This is phi x y z equal to c level surface, and the gradient at this point p, suppose not zero vector, then this grad phi is a vector normal to the surface, that is perpendicular to the tangent plane at the point p, normal. This is the geometrical interpretation or meaning of gradient. The unit vector normal to the surface phi x y z equal to c at any point on it is given by n cap. Normal vector, let us denote by n cap, is equal to grad phi divided by magnitude of grad phi, modulus of grad phi. Vector divided by its magnitude is unit vector, we know, provided of course grad phi is not a zero vector. Now grad phi equal to I del phi del x plus j del phi del y plus k del phi del z at a point px on y and z1 is a vector normal to the level surface phi x y z equal to c through the point px on y on z1. Okay, therefore del phi by del x plus del phi by del y plus del phi by del z means the partial derivatives with respect to x, y and z are direction ratios of the normal to the surface at the point px on y and z1. We know coefficient of I cap, j cap, k cap in a vector are the direction ratios of the vector. So here partial derivatives are the direction ratios of the vector grad phi, but grad phi is normal to the surface, so they are the direction ratios of the normal to the surface at the point considered, and hence the equation of the tangent plane to this surface at the point x on y and z1 is given by x minus x1 into del phi del x plus y minus y1 into del phi del y plus z minus z1 into del phi del z equal to 0. We know if a comma b comma c, small letters a b c are the direction ratios of normal to a plane and the plane passes through x1 y1 z1 point, then a into x minus x1 plus b into y minus y1 plus c into z minus z1 is the equation of the plane. So that we have written only here instead of a b c, here del phi by del x, del phi by del y, del phi by del z. So this is equation of tangent plane to a surface phi x y z equal to c. Also the equation of the normal to the surface at the point x on y and z1 is given by normal. Equation of normal is a straight line, and in symmetrical form equation of a straight line is x minus x1 by l equal to y minus y1 by m equal to z minus z1 by n. Element are the direction cosines or direction ratios of the line. Here direction ratios of the normal are partial derivatives, so that's why equation of normal to the surface at the point x on y and z1 is given by x minus x1 by del phi by del x, y minus y1 by del phi by del y, z minus z1 by del phi by del z. Okay, so this is equation of a straight line in symmetrical form. Okay, where the values of the partial derivatives at the point x on y and z1 are to be used in the above two equations. That is important because we are finding a tangent plane and normal at the point x on y and z1. So partial derivatives value should be used at the point x on y and z1. Now let us see some examples. Find the unit vector normal to the surface, this surface 2x z square minus 3xy minus 4x minus 7 equal to 0 at the point 1 comma minus 1 comma 2 on it. This is a point on this surface. Also find the equations of the tangent plane and the normal to this surface at the point 1 minus 1 2, means at the same point. So unit vector will be given by the grad phi divided by magnitude of grad phi. So let us see what is phi here. So given surface is this equation is the equation of the surface. So left side let us name as phi xyz. So phi xyz equal to 2x z square minus 3xy minus 4x minus 7 equal to 0. So this is phi, so this is equal to 0, our surface phi xyz equal to 0. At the point 1 comma minus 1 comma 2 means at this point Here x1 and z1 is are 1, minus 1 and 2. Let us find all the partial derivatives. So del phi del x. See, partial derivative with respect to x means y and z both constant. So if we differentiate this line, if we differentiate this phi xyz with respect to x, it will be 2z square minus 3y minus 4. 2z square minus 3y minus 4. Okay. So if we put 1 minus 1 to 4 xyz, we get 2 square 4 8 plus y is minus 1, so plus 3 minus 4 is 7. Okay. Now del phi by del y, if we differentiate this line with respect to y, what we get? This is 0, no y here. Here it will be minus 3x only, so minus 3x, and x is here 1, so it is minus 3. Del phi by del z, partial derivative with respect to z, it will be 2z means 4xz. Okay, and no z, 0, so only 4xz. If we put x is 1, y is 2, you get 8. So you have got partial derivatives at the point 1 minus 1 2. Now grad phi is I del phi by del x plus j del phi by del y plus k del phi by del z. I, j, k are unit vectors. So putting the values here, 7 minus 3 and 8, we have got this as the grad phi. Therefore mod grad phi is root over 7 square, coefficient of I square, coefficient of j square, coefficient of k square. Okay, so 7 square plus minus 3 square plus 8 square, we are getting root over 122. So therefore required unit vector normal to the surface is n cap equal to grad phi by mod grad phi, that is 1 by root over 22, 7 I cap minus 3 j cap plus 8 k cap. Okay, of course directly we can find grad phi here instead of finding individual partial derivatives for finding unit vector. But why we have done? Because we shall use this values of partial derivatives for finding equation of tangent plane and normal. Okay. So unit vector got. Now required equation of the tangent plane is given by x minus x1 into del phi by del x plus y minus y into del phi by del y plus z minus z1 into del phi by del z equal to 0. Here values of partial derivatives are 7, minus 3 and 8, and x1 and z1 are 1, minus 1, that's why it is plus 1, and 2, z1 is 2. So we have got 7x minus 3y plus 8z minus 26, 0. This is equation of tangent plane at the point 1 minus 1 2 to the given surface. Also required equation of the normal is given by x minus x1 by del phi by del x, y minus y by del phi by del y, z minus z1 by del phi by del z, means x minus 1 by 7, y minus minus 1 means plus 1, by minus 3, z minus 2 by 8. So equation of tangent plane, normal, unit vector normal to the surface, all are obtained. So one example homework, find the equations of tangent plane and normal to the surface, this surface at the point is similar to previous one, you can do. Next one theorem involving gradient. If f of xyz and g of xyz are two differentiable scalar point functions, then gradient of c equal to 0 vector, del c equal to 0 vector, where c is a constant. Gradient of a constant scalar point function is 0 vector. Gradient of cf, del cf equal to c del f, c into gradient of f. Okay, constant can be taken out, c is a constant. And gradient of sum or difference of two scalar point functions is sum or difference of their gradients. Then gradient of product, del fg equal to f del g plus g del f. First function into gradient of second function plus second function into gradient of first function, like our u into v rule of derivative. Then gradient of quotient f by g, it is g del f minus f del g by g square, like our quotient rule of differentiation. Okay, so let us see proof of some of them. Del c, gradient of c equal to I cap del c by del x plus j cap del c by del y plus k cap del c by del z. But c is a constant, so all its partial derivatives are 0. Therefore I0, J0, K0 means it is 0 vector. Okay, gradient of a constant is 0 vector. But we note that the converse is also true. That is, if gradient of phi is 0 vector, then phi is a constant, phi equal to c. We can see the justification here. Suppose gradient of phi is 0 vector, means I del phi by del x plus j del phi by del y plus k del phi by del z is 0 vector. Therefore, if a vector is 0 vector, then all its components are also 0, means coefficient of I cap, j cap, k cap are separately 0. So del phi by del x 0, del phi by del y 0, del phi by del z 0, scalar 0. That means phi is independent of x, phi is independent of y, phi is independent of z. All partial derivatives are 0. That means phi does not contain x, y, z, means phi is a constant. Therefore, phi is equal to c, a constant. So the converse is also proved. And let us see number 5. Others can be proved similarly. Gradient of quotient f by g is, in short, let us write summation I cap del by del x of f by g. But this is derivative. So quotient rule of derivative we can use partial derivative. So g square means denominator square, denominator into derivative of numerator minus numerator into derivative of denominator. Okay, summation I cap. Now g square is independent of summation, so taken out, and then summation I cap into g del f by del x minus f del g by del x written. Now summation is distributive, that's why, and also g can be taken out of the summation here. So it is g summation I cap del f by del x minus f into summation I cap into del g by del x. But this is del f, gradient of f, and this is gradient of g, del g. So therefore the result is proved. Okay. Now let us see what is angle between two surfaces. The angle between two surfaces at a common point is measured by the angle between their normals at that common point. In case of curves, the angle between two curves we measure by angle between their tangents. In case of surfaces, actually we define angle between two surfaces as angle between their common tangent planes. Here this two dotted lines shows their tangent planes to the surfaces at this common point. Okay, at this common point, this is a common point. Now this angle between two tangent planes, that is angle between two planes, all of we know angle between two planes is also measured by angle between their normals. That's why finally angle between two surfaces is measured by angle between their normals. But we know the normals to the surfaces are given by gradient of the corresponding scalar point functions. So that's why angle between that normals means grad phi and grad psi will give us the angle between two surfaces. That's why in the definition also it is written angle between two surfaces at a common point is measured by angle between their normals at that common point. So one example let us see on that. Find the angle between the surfaces x square plus y square plus z square equal to 9, a sphere with center origin radius 3, and x square plus y square minus z equal to 3 at the point 2 minus 1 2. This surface, this sphere, we have to find the angle between them at this common point. Okay, given surfaces are, first one is x square plus y square plus z square equal to 9. Let us name it phi xyz. So we can write it phi xyz equal to x square plus y square plus z square minus 9 equal to 0, means changing 9 to the left side, that is phi. So phi xyz equal to 0 is the surface. And second one, let us write psi xyz, x square plus y square minus z minus 3. If we write, that will be 0. So psi xyz is these two surfaces. Now at this common point 2 minus 1 2, let us find grad phi and grad psi first. So grad phi, del phi is I cap del phi del x plus j cap del phi del y plus k cap del phi by del z, that is del phi. Phi is here, x square means 2x, then del phi by del y will be 2y, del phi by del z will be 2z. Okay, now if we put 2 minus 1 2 here, we get 4a cap minus 2j cap plus 4k cap. Grad phi we have found. Similarly, grad psi or del psi is I cap del psi by del x plus j cap del psi by del y plus k cap del psi by del z by definition. So here del psi by del x is 2x, del psi by del y is 2y, and del psi by del z is minus 1. So then we put 2 minus 1 2 for x, y, z. Z is not here, of course. So we get 4a cap minus 2j cap minus k cap. This is grad psi. Means this grad phi is normal to the surface number 1 and grad psi is normal to the surface number 2. So let us take the dot product. So grad psi dot grad phi dot grad psi is equal to, the values are substituted here, and then dot product means coefficient of I, j, k are separately multiplied. So 4 into 4 16, minus 2 into minus 2 4, plus 4 into minus 1 minus 4, so 16. So grad phi dot grad psi, dot product of the normal vectors, is 16, but by definition we know it is mod grad phi into mod grad psi into cos theta, where theta is angle between grad phi and grad psi, the vectors grad phi and grad psi. So it is root over 4 square means 16, 2 minus 2 square means 4, again 4 square 16. So second one is also 4 square minus 2 square, 1 minus 1 square. Okay, 16. Then this is 6 root over 21 cos theta 16, means cos theta is 16 by 6 root over 21, means it is 8 by 3 root 21. Therefore theta is cos inverse 8 by 3 root 21, and this is the required angle between the given surfaces at the common point 2 minus 1 2. So we have found the angle between the surfaces. So this is just an introduction to vector calculus. We shall see vector field, vector point function, their divergence, curl, etc. in the next lecture. Thank you.